Hi all, Mads Barnkop from Kaizer Powertrains here. Today we're taking a look at part 2 of the UD3 driver video, and this is in the series of getting started with the UD3. So now we're going to look at how to implement this driver into an actual coil. The topics that I want to go through in this video is look for a new firmware update and do an update of the driver board. Then look at what do we need to change on an existing coil that uses a UD 1.3 or UD 2.x driver. There are some minor things we need to adjust, and then look into the software part where we can do tuning, we could do frequency sweeps, and see what kind of capabilities do we have with the UD3 driver. I hope that by the end of this video has earned your like and subscribe. Every comment on this video will be answered, so please leave your comments down below. Tesla coils, high voltage, this project, anything. So let's get going. I normally consider my Tesla coil here to be a small Tesla coil. Part of my head I'm thinking about this as a tabletop Tesla coil, but once you get it on the bench with the secondary coil, it would hit the ceiling by now. The existing hardware that we will have to replace is this Arcatech DRSSTC driver from 2012. So that is a good 12 years old by now. Now, I forgot I had this in. This was changed out when I blew up my previous bridge on this, and I had to change it very quick before I show, so you can check out that video. There's a link in the description, and also pops up somewhere right over here. Now we can see here that it uses a 10-turn overcurrent detection setting, and I have set it for 3.5 volt for 750 amp on these SKM 200 IGBT bricks, and the feedback and current measurements, or the overcurrent detection, uses two 1:1000 ratio current transformers sitting over here, and we have a single GDT with 4 outputs and a single primary. We already know that we will have to change is the current transformer ratio will likely need to be changed, and the GDT will have to be rewinded into 2 separate GDTs. Now I have my core, which sports 96 square millimeters of cross area, and it is rated for a permeability of near 6000. Now the resonant frequency of the DRSSTC1 is 70 kilohertz. And for now we're just going to use an example of the gate chart of a CM300 brick. It's in the high end, but as we can see, it only calculates the current needed for the IGBT drive, so it doesn't really matter for the GDT calculation. We can use Cat5 Ethernet cable, as that is 0.2 square millimeter cross section, and that gives us a low enough resistance that we avoid any serious droop and voltage loss. And as we can see, we might even want to add some more turns just to get higher above the saturation limit. And actually doubling the figure is quite normal if you want to use something like pulse skipping or other places where you have very long on times. It's very normal to say that you go with something around 100 square millimeters, around 5000 permeability, and 10 turns, 24 volt DC drive, and you have a run-of-the-mill gate drive transformer. For winding gate driving transformers, I really do like using old Ethernet cable. We needed 2 times 80 centimeters for our 2 gate drive transformers. And then we can get rid of this whole bundle. I gave myself 15 centimeters of leeway for each lead end, so that is about here. What I would really do is just to make 10 loops, and then let's call that 10 windings. Calculating 5 centimeters per turn were pretty darn precise. So here we have it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 turns, and then we'll just unwind the twisted pair here, and then wind them back into each their respectable color pairs. And now I have a nicely winded gate driving transformer here. The two white wires running in parallel. So we have double current handling on the wire here on the primary, and for each secondary we have a single color pair here. And we have the phasing marked, so we know how, on the primary it doesn't really matter, but on the secondary side we want to change one of them over for a half bridge. Back at the GitHub repository, we can see that the latest TeslaTerm integration release is from April 1st, 2021. So that is a good 3-year plus old by now. So if you want to try out your own firmware or some of the experimental firmware that is in the repository, there is a few ways to do that. Now, if we look at the front page here, we can scroll down to the documentation, and we can see here the installation is compiled with PSOC Creator, a link, and flash to the precompiled binaries. So that's the releases mentioned earlier. There's a few other options to flash the firmware. And while this looks like the main documentation, we actually have to go to the wiki page. The wiki page is a bit more updated than the front page, and here we can see that the bootloader is now with USB support via TeslaTerm. But there is no documentation of how to do that in the UD3 repository. For that, we will have to switch over to the TeslaTerm repository. On the front page, there is not much to see, so we have to go to the wiki page as well. And we should be able to find something here under bootloading. And it says here that it is possible now to drag and drop a compiled binary onto the TeslaTerm window, and by that you can upload it. It is also mentioned here that you can do upload through the FiberNet connection, but that is dependent on the version. And for these lower versions, you will have to use the FiberNet onboard FTP, which is kind of another undocumented feature, but we can find that in the repository. So if we go back to the UD3 and we look the repository again, and we'll have to look into the TQFP folder here, and there is a text file called ftp.txt, and here is a small script where you just have to replace the IP address along with your image file, and you can flash it through the FTP server of the FiberNet. And if you want to build the software yourself and not use the binaries, you will have to download PSOC Creator, which is currently at 4.4 version, and compile the code yourself and build your own binary to upload through the 3 different ways I just mentioned. To give a link back to part 1, we went through the getting started part here, which were through the build notes. We flashed the firmware, or the firmware was actually flashed for me to start with, but now we went through how to do that. We went through the testing page to verify operation and that we connect and get a network connection. We connected to the UD to our coil, not completely, with some sensors. And now we made the gate drive transformers. Now we want to make sure that the current transformer for feedback and overcurrent detection is also suitable from the DRSSTC 1. And it's noted here that we need to have a feedback transformer which results in 1.5 amps at absolute peak current. Now I also made a standard 1:1000 ratio current transformer, so that means that I could have a maximum of 1500 amps in my primary circuit, so that is no problem using the original current transformer. I'll just actually have to remove one, because in the older drivers we had 2 current transformers, one for feedback and one for overcurrent detection. Here the driver uses only one for both jobs. Let us first fire up TeslaTerm, and we're connecting min over UDP. Delete localhost. It searches your network for the UD3. We connect to it, we get the 23 degrees Celsius right away, so we know we are connected. Do the TR start for starting transient mode. And we should have output on the oscilloscope. The second row here, that is the first IGBT, or the upper one, and the upper one here is the lower one. And it's connected to the oscilloscope through two differential probes in order to not short out the ground. As we can see, we measure on the gate and the emitter. And that becomes a problem if you connect your ground clip here, and you also have a ground clip down here. So that's why you need two differential probes to measure the two upper IGBTs. The GDT1 A and B is on channel 1 and 2, and GDT2 A and B is on channel 3 and 4. So we should see 1 and 4 switching on the same time, and 2 and 3 switching on the same time. So let's check out the oscilloscope here. As we can see, we have 1 and 4, they should be the same. And they are. That's good. And then we have 2 and 3, which should be the same, but they're not. Only channel 3 is opposite, so we have a phasing error on channel 2. Channel 2 would be the lower part of the IGBT, which would be this one. So even though I did mark this up quite rigorously and kept track of it, it seems that phasing is still wrong on one IGBT here. So let me just correct that. A good sanity check to do when changing the phasing over here does not work well tells us it's something with our measurement. And quite right. If I look through my settings here, then channel 2 has invert on. And I discovered this by taking my differential probe here, and the other one is a 2-channel isolator sitting up here on the bench, and just connecting that up to channel 2 and got the correct setting, or the correct signal. So that was just a setting on the oscilloscope. It is a little cramped down here at the inverter, but I have my 4 gate connections here on the IGBT bricks. The pink and black wire sitting over here is the DC bus measurement. They have put in series with 700k ohm resistors, so that can sense a maximum of 700 volt DC. That's 100k per 100 volt as per the documentation. And as I'm running rectified 400 volt AC, that is around 560, so that fits very well. The current transformer sits here on the positive bus bar from the DC link. Error towards the load, so I hope that's right, else I will have to take all this apart again. The gate drive resistors are 4R7 1 watt metal oxide resistors. Let us connect to the UD3, and we are connected. We have to set up the new DC bus voltage measurement. We can go into settings, and we can say that our tuning start here will start at, this Tesla coil resonates at 70 kilohertz, so let's just start at 60 and end at 80. We'll tune at the 50 pulse width, or that must be the microseconds, since it says 800. Some delay, noise deviation, watchdog. Some different settings that we do not need to use right now. Our bus, okay, so this is what we need to change to 700. The resistance for bus voltage measurement. And the good thing about this one here is that we can actually save it to UD3, and we can send and save to EEPROM. So by only clicking send to UD3, it is only written down into the session we are in now, and a new power reset or power cycle of the board, and we are back to the normal settings saved in the EEPROM. So this is a very safe way to try out settings, and if it doesn't work, then you can just reboot your driver. So let's see, CT ratio here, CT1, that is 1000. But I'm not quite sure about CT2. Max transient current, 750. I'm not sure that I have to save every time between a tap, but I'll just do that now. It is also possible to change the gauges out here to see temp 2, for example, but there is no way of saving these in this version, so they will always reset on a new power cycle of the driver. So let me just use a variac to put some voltage on the DC bus, and we can try to do a auto tuning. I have placed a piece of metal inside the primary for this. We're not seeing any voltage on the DC bus right now, despite that I did turn it up to 50 volt AC. Do a tune primary. Okay, very nice. So we found a peak at 65. Is that where we started? Got a feeling that something is not right there. Let's see our settings here for the auto tune. Yeah, tune start 60 to 80, okay. So 65 is actually not that much off where it's tuned today. But we could widen that, that setting a bit. So let's say we try from 50 to 100 instead. And we'll run a tune primary again. Okay, that's a much nicer graph where we can actually see our two peaks. Using the signals command, I could see that the VBAD was getting an input voltage and not our VBus. So apparently the connector on the UD3.1 PCB is different between the VBus input and the battery input on the connectors compared to the UD3 PCB. I ran into some problems with the UD3 firmware not being able to run with the current version of TeslaTerm. So Malte compiled a newer version of TeslaTerm for me, but that also needed a new UD3 firmware. So I was very lucky that he also compiled that for me and saved me a lot of time of setting up the IDE for doing that myself. So let's connect to the UD3. And by now it should just be dragging and dropping the compiled binaries onto the UD3. So let's try that. Yeah, that triggered a lot of errors. Not sure if that was good. Let's just try to reset it. Okay, so we're at the same build still. In order to use the FTP upload, we need to insert a SD card into the FiberNet MIMI storage. So making a joke of that in my first video caught up on me here trying to do the firmware update. The SD card is mounted in the FiberNet, so let's connect up to the UD3. And now it should just be as simple as drag and dropping the new binary onto TeslaTerm. Okay, so it's throwing a lot of alarms now. Failed to send frame, attempting to reconnect, and it reconnected. Oh, a lot of tasks starting up, so that's the whole booting of the driver. But as we can see now, built August 10th, 2024. So that was made yesterday by Malte, and I thank him very dearly. And now we have graphs running. When we have the TeslaTerm open in the menu, we have something called Save Flight Recording. And that gives us a zip file. And we can open up the TeslaTerm again, the connection window, and we can drag the zip file onto here, and we get a look into the log file. So here you have all your events listed, and you can go into the telemetry window where you actually have a time slider. So you can replay any moment that happened within, I think this will record something like the last 10 to 11 minutes, it seems. So if you have a catastrophic failure, you can actually replay the waveforms and see where something went wrong, and yeah, maybe you have some clues in your measurements here. So a very cool feature of TeslaTerm. Right now we have data coming into the TeslaTerm, so let me turn up the voltage. We're going for 50 volt AC input, and we can see the DC voltage at the top here is at 70 volt DC now. So we can try to do a tune primary. We get a warning that the voltage is high due to being 70 volt and not 50 volt, but these are large IGBTs, they can take it. As we can see, they are only hard switching around 100 amps. But we're not getting the plot now. Let's try to play a MIDI song that we all know on a iron dummy load. I hope you all enjoyed this video, part 2 on getting started with the UD3 Universal Tesla Coil driver. It is capable of so many things, and even in this video, despite having hours and hours of raw material, I could not cover all the settings and parameters that this is actually capable of. There is a huge amount of work done by Jens, Malte and Torben, and I cannot thank them enough for making this open source and sharing all their knowledge and software, hardware, design, everything. And even on top of that, you can get help directly from them on the Discord channel that you can find in the link down in the comment section. So please do leave a comment on this video if you have any questions about getting started with the UD3, and I will help you as well. Please like and subscribe to the video. Subscribe to the channel if you really like the videos. Share it with your friends. I really would appreciate that. So until next time, see ya.